So for today, we are going to discuss the third part of the moment distribution video series. So today we are going to discuss a frame example. So basically, you know how to deal whether it is non-sway or sway frame, right? So this will be the example, and please go through each video. So this is the first video, second video on sway and non-sway frames, and sway frames, right? So these are the very basics, where you can 100% learn moment distribution with examples as well. So links are in the description. So please go through before this video. So for this example, we're going to be dealing, so you can see this frame is fixed at A, fixed at E, and fixed at C. There's no way that this frame can move in lateral direction due to this fixed support, right? So even no lateral loads are present, right? So that's another different story, but loading is asymmetric, but the frame cannot move in lateral direction, so that it becomes a non-sway frame, right? So first we need to determine whether it is the joints are uh, fixed, continuous, or discontinuous, right? So we know anyway fixed gonna be fixed, right? So this is very simple, and there are three members. That means three bending moments at the joint, right? So in the first or second video, I showed you if there are two or many members, there will be uh, sigma m should be 0, right? So that means it's a continuous one, right? If one bending moment is there, right, m is 0. In that case, if there's only one member, that is a discontinuous, right? So since there are three members connected, then you know at this joint sigma m should be 0, right? So that means a continuous joint. There are two members. That means this is also a continuous joint, right? Please check the video 1, 2, 3. You will understand the concepts, how to get these fixed and continuous, right? I have fully described those. So if fixed to continuous, I have told you it is for EI over L, right? Even fixed, so fixed to continuous and continuous to continuous as well. So here the EI is a constant, right? So here also for EI over L is also for EI over L, right? So L is given as 16, right? 16, 16, right? This is LEI for EI over 2L, right? So you can determine this is for EI over EI is constant and given. So this is 16. This is also for EI over 16. This is also for EI over 16. This is for EI over L is 12, right? Okay. So we need to determine which percentage of bending moment each member will take, right? That is proportional to the distribution factor, right? You know, at the fixed and distribution factor is 0. I have told you the reason in the first or second video. You can see. because according to the distribution factor, that's going to be K, this member, plus there will be some member inside this portion that is going to be infinitely stiffness, right? Because of fixable, so something divided by infinite is 0, right? And this is going to be EI over 3, right? This is going to be, everything is going to be EI over 4. Right? Okay. So since this stiffness is same for these two members, the distribution factor will be 0.5 and 0.5. So you can take each member, that's EI over 4 divided by total stiffness at that joint, EI over 4 from this member plus this member, that is also EI over 4, right? So this I will get it. So this is going to be EI over 3 divided by EI over 3 plus this member EI over 4 plus this member EI over 4, right? That's going to be EI over 3 plus EI over 3 plus 2 into, there are two members with EI over 4, that joint, right? So that means your stiffness is going to be, let me check, 1 over 3 divided by 1 over 3 plus 4 plus, so that's going to be 0.4. So the remaining part is equally distributed within these two members. That's going to be 0.3 and 0.3 because the summation of distribution factor is 0. That simply means if you add something bending moment, this portion will take 40%. This is claiming I can take 40%. That means 0.4. This tells you I can take 30% of that. That means 0.3. This tells you I can also take 30% of that. If you add the bending moment to this joint, there are only two members. He is telling I will take 50%, and the remaining 50% it's taken by this member, right? Okay, so this is the simplest form, and you can determine the L is 2L, and I will take this figure. So we can determine stiffness AB is what? It's 4EI over L. That's going to be 4EI over 2L. Right? 4EI over 2L. Then each stiffness of KEB is equal to KEB, then BC KCD is equal to 4EI over 60, right? Right. So this is stiffness, right? Distribution factors at A, right? So at B, at A, the distribution factor is 0, right? There's only one member, A. It's going to be AB, distribution factor AB, right? Right. At B, you have BA and BC and BE, right? These are all at B. Right. You have 3 members at B, right? I will merge this. Right. And also you have 2 members at C. And 1 member at D and E. Right, that's BA, you remember it was 0.4, right? This is going to be 0.3 and 0.3. Here you have C, D and CB. CB and CD both 0.5 and 0.5, right? The equal stiffness. That's what. And D is again 0 and 0. I is a fixed support, right? EB and DC. Now it's done. Distribution factors are okay, right? So the fixed moments, then at A, you have MF AB, right? At B, MF BA, right? And BC, MF BE, MF CD, MF CB, MF DE, F, right? So one thing you can do is, now you can, these are not the fixed moments, okay? So the value is it's a UDL, right? So that's going to be WL squared over 2L. So W is 2 and L squared is 2L squared over 2L, right? So that's going to be 24, right? At A it is our sign convention is clockwise positive, right? Sign convention is clockwise positive, so the anti-clockwise 24 and clockwise 24. It's going to be minus 24. This is plus 24, right? At BC, you have point load that's going to be PL over 8, right? So your P is 10, L is 16 over 8. That's going to be 20. Minus 20 at B and plus 20 at C. No other, so CD, sorry, B, not B. Yeah, it's going to be, and CB is 20. MFBC is this, MFCB is this, right? CD is this one, and BE is this one, it is 0. DE is again no loading, that's DE, not DE, DC. DC is again 0, this part. EB is again 0, right? So you can start the table now, right? I will start the table. Okay, so you can start it from A. A, then E, then C, then D, then E. That you have AB, 3, 2, and E, B, right? So your distribution factors, you have 0, 0.4, 0.3, 0.3, and CD is 0.5, it's 0.5, 0, 0. So I'll draw in the red color because it is not need to be added to the final equation. So FEM, fixed end moments, this is going to be minus 24. This is going to be BA 24. This is BC 20 minus 0. CD is 0. CB is plus 20. This is 0 and this is 0. Right? So now you can start balancing. I'll start balancing. So fixed, this is fixed, right? Fixed, continuous, this is also continuous, fixed, fixed, right? So you know from the theory I taught you, you don't need to do any damn thing for the fixed support, right? That will be already there. You only need to balance continuous or discontinuous. Since in this case you don't have any discontinuous cases, so you can go ahead and balance the continuous ends, right? Okay, so this thing you can start balance B. I'll start balance B, right? So B telling me there is already 24 minus 20. That means 4. Positive 4. Positive 4 is the unbalanced bending moment. We have to balance that. To balance positive 4, we have to add negative 4, right? That means anti-clockwise 4. And if I add anti-clockwise, BA telling I can take 40%, BC telling I can take 30% of that, BE telling I can also take 30%. So this is the balance bending moment, negative of addition of these two. Addition will give you 4 and negative is negative 4. And that has to be locked. That value is locked, right? Multiplied by the distribution factor. How much each member take? How much BC take? How much BE take? Right. So addition of these two will give you again minus 4. These three, right? So moment you did that, you need to start carry over. Carry over moment, right? So BA is continuous. Its neighborhood is AB. Carrying over is always done within the same beam, same neighborhood, right? If it is BA, BA's same neighborhood is AB, right? You need to swap the letters. BC's neighborhood is CB, not BA or any other, right? BE's neighborhood is EB. You need to just swap the letters, right? BA's neighborhood is AB. So it is from continuous to fixed, right? So I told you if it is fixed to continuous, you should give half, right? Continuous to fixed, you don't give anything, right? Continuous to discontinuous, you don't give anything, but discontinuous to fixed, sorry, discontinuous to continuous, you should give half, and continuous to continuous 0.5 in either direction, right? Remember, if it is discontinuous to fixed, there's only one span, or discontinuous to discontinuous, that is determinate, right? So no need to worry on those cases. Discontinuous to fixed and discontinuous, no need to worry. So fixed to continuous, you should give half. Continuous to fixed, you do, sorry, fixed to continuous, the other way around, right? Continuous to discontinuous, you should give half, right? This is the distribution. Carrying over fraction, right? So fixed to continuous, you don't give anything, right? Continuous to fixed, you should give half. Discontinuous to discontinuous, you don't give anything. Discontinuous to continuous, you should give half, right? Okay, so this is from continuous to fixed, you should give half. This factor is always half for your cases. Okay, carrying over done. BC, continuous neighborhood is CB, also continuous, you should give half. BE's neighborhood is EB, and that is fixed, continuous to fixed, you should give half. It's done. Now B is balanced. Now C is still unbalanced. So unbalanced bending moment is balance C. Unbalanced bending moment is 20 minus, so that's going to be 19.2. You have to add minus 19.2, that will give you by this, right? Sum, what whatever at this location. Can see 19.2. You have to add 19.2 because the summation is positive 9.2. You have to balance that. You have to add negative 19.2. And how you're going to add that? You multiply it by the distribution factor. That way, CD will take half of that. CB will take half of that. Right. So moment you done, you have to carry over. So CD's neighborhood is DC. DC is here. That's going to be continuous to fixed. So you should give half. This is going to be CB to BC. Continuous to continuous, you should give half. So then again, B is not balanced, right? So you have to balance that B. So now you have, either you can take all of this summation, let's say summation of all of these will again give you 4.8. Why? Because this is already balanced. If you add these 6 together, it is 0. So only you need to balance what's added in the previous step, right? That's minus 4.4. You can see addition of this is balanced because we balanced that, right? In the previous step, you only need to balance. You only need to balance this one, and you have to add the negative value of that. You have to lock this value. Otherwise, it will change when you drag the formula. That's why I lock it. Multiply by distribution factor. Right. So you have to carry over. I just copy the formula. Right. Yeah, I think I did a mistake because to balance BC, you have to take CB, okay? It's 0.6. I have taken it from BA, balance it. You can take it's correct. BAAB, CBBC, okay? EBBE, okay, right? So now it's okay. Okay, so you can start balancing again C. Now C is not balanced. So you can add the negative value of additional bending moment, lock it, multiply by distribution factor. Right? Then you can carry over. Right. So you can again balance B. Now this value is this is what additionally taken. Okay, you have to add according to the distribution factors the negative value of that to balance this joint, because this is now already, this is initially balanced, this was balanced. That means all of this is balanced again. If you add this, it is 0. If you add this part, it is 0. If you add all of these, again it is 0, because each part is respectively 0. So you have to balance only this amount, right? So then you have to carry over. Okay. Then you can balance C. Negative value of that to the carry over C. So again, it's B. There's a reason why I'm continuing still, even with sufficient accuracy. I'll tell you the reason later. Multiplied by the distribution factor. And then C. Can again balance B. I'll stop from this balance. So it's good practice to always stop from the balance moment, balancing step, because if you carry over, there will be again an unbalanced bending moment, right? So you bring an unbalanced bending moment to forward, right? So stop at the balancing step. Okay. So I can take the final moments. So don't now add these things in red color. Those are distribution factors, okay? Summation of the each column. That's very simple. Okay. So you can see everything is under balanced, right? So B joint is balanced. If you add these three, it's balanced, right? So if you add these two, C joint is balanced. There will be an unbalanced bending moment at the fixed end. That should happen, right? So where did I stop? That's a question. Even you can stop it from here, right? You can stop it from here because sufficient accuracy, right? So let us check what actually happens from each step, right? So when I first balance that, I can take the moments, right? Can take the bending moments. It's like this. So when I first balance that, so at least you have to balance one step. When I first balance, so you can take from this step summation to this, right? Okay. This is the first step. Right. This is the balancing. First step. Okay. So this is my second step. Summation of when I balance C, right? This was first step, this was second balancing step, right? This was third balancing step, balance B. This was fourth balancing step. This is 5th balancing step, right? This was 6th balancing step. Am I right? Yes. This was 7th balancing step. This was 8th balancing step. This was 9th balancing step. You can see how view accuracy changes. Right? So if you draw a graph, you can see with from 4th to 5th step, so you can see 6th step, it's converging, right? So if you draw a line, you can see, right, for AB, right? This is for, let's say, BA. That's also converging, right? You can see it's converging to 24.5, right? So from 6th, almost 5th step, right? Right, let's say fix end, this one, CD. So you can see it started from 0, so it's converging to 10.79, right? Right. So even if you take this table, so you can see it's converging to 5, right? So you take these values, so you can see it's even converging from 5th step, right? Even 4th step is sufficient, right? Sufficiently accurate. So where to stop that? That's a good question. That depends actually on the original fixed end moment. Can you see? So compared to these values, when your error is, right, when your error is at least 100 times less, that means 1 over 100, right? That's going to be 1 decimal place. When your error is still digit is there, right? So from this moment, your error is getting, so whatever the bending moment shared or balance will be 1 decimal. So that means 1 over hundreds of these values, right? Right. Error is getting significantly lower compared to the original fixed moment. You can stop, right? So you can see for 1, 2, 3, 4, right? 4th step, error is getting significantly lower. Then you can stop, and those answers are sufficiently accurate. You can see, even if you take to 9th step, there won't be a big difference. So that depends on your judgment whether to stop. That means compared to a original fixed moments, whatever balanced at a particular step are significantly lower or not, right? right? If you're fixing something like 5, 1, 2, 3 likewise, then you have to at least go for second decimal place, right? So there's a pattern, right? So hope you understand that. So thank you very much. So these are the final support bending moments, right?